In a companion video, I introduced the concept of 802.11n and the key benefits, the key mechanisms and the key benefits. The mechanisms were at the RF layer, the PHY layer, and the MAC layer. And really what it does is make sure that in an indoor environment in particular, where there are a lot of reflections and different beams coming in from a sender to a receiver, it tries to optimize the channel. And we talked about the benefits being approximately 10x increase in capacity, 2x increase in range. That's the good part. In a home environment, there is really no downside to migrating from ABG to 11n. But in an enterprise, when you're thinking about designing a wireless LAN network based on 11n, you have to be careful about a few key things. So let's talk about what they are. The first one is that even though 11n overall is much better than ABG, it is significantly more unpredictable. If you look at this graphic here, you'll see that even though the rates are significantly higher, the profile of these rates is much more unpredictable. It's much more spiky and erratic. So in other words, if I'm just sitting here 20 feet away from an access point, I know I'll do better than I would have done in ABG, but I really can't tell whether I'll get 300 megabits or 180 megabits. What's more, if I sort of move my laptop around or walk a few feet, I might get a completely different profile. And the reason is, it all has to do with how the receiver is combining reflections. Sometimes reflections are constructive, sometimes they're destructive. And notice that we are talking here about wavelengths in inches. We are not talking about wavelengths in feet. So even a movement of a few inches can dramatically make or alter the user profile or the data rates that you receive. The fundamental takeaway is that 802.11n, in terms of predicting precisely what sort of rate and range you get, is much more unpredictable. The impact of that in a multi-AP enterprise wireless LAN is that it's much more difficult to predict co-channel interference. If inherently the signals are very spiky and they're time variant, how do you know when two access points are interfering with each other? Very difficult to predict that a priori. And in fact, all radio management tools and the microcell concept of trying to design away co-channel interference is quite fundamentally broken in 802.11n. So that's the first significant point you need to be aware of. What worked in ABG in terms of being able to predict and manage the channel is not going to work in 11n, because you can't predict and hence you can't design or tune around it. The second key point, I extolled the virtues of the burstiness of 11n in a companion video where we talked about the core technology, right? So we talked about the fact that in one contention round, we were able to send many frames. That's a good thing. However, if you see any loss, notice that now you're not just going to lose one frame, you're going to lose a bunch of frames back to back. And what's more, at the end of every burst of data, there is a single block ACK, as you see from the graphic. Now, if it turns out that you lose this block ACK, even though you might have got all the data, it's all effectively lost from the sender's perspective. The sender has to retransmit all the frames. This has two implications. First, loss of block ACK, even in unicast, is very bad. But the second, notice that when you're doing multicast traffic, you have one sender transmitting to many receivers, so there is no acknowledgement. And therefore, multicast is liable to be significantly more lossy. In fact, in general, 802.11n operates in much higher loss profile than 802.11 ABG. In a clean ABG channel, you could bring the loss down to about 3–4%. But with 11n, typically you're operating in a regime where the loss is more than 10%. Now, it doesn't matter overall just because the channel has higher capacity and retransmits make up for it, but watch out for the fact that retransmits are going to be much more bursty, and when you do multicast, it's dramatically different because there is no retransmit. Therefore, multicast is going to be more lossy and it's going to absorb more burst loss. There's another subtle point that I'm not going to cover in this video, probably requires a whole session on its own, which is the implication of rate adaptation on 11n. If you simply take existing ABG rate adaptation mechanisms and port it to 11n, ain't going to work. And the reason again is, recall from the graphic here, 11n losses are likely to be much more bursty. And the way 802.11 ABG rate adaptation algorithms have historically been used, they use loss as a measure. It's a very different thing losing 10 packets in a row every 100 frames as opposed to losing one every 10. Right? This burstiness completely changes the way one needs to think about 802.11n. That's the sort of core technology implications.